All right. So we are going to introduce quantum mechanics. Um, so my background is in biology, right? And I didn't do any physics in university. I did 1 year of calculus. So the last time I did math, physics or math in university was, oh man, 1990. So this is my attempt to explain quantum mechanics to you kids. I've been looking at this material for the last several years, and I must admit, initially I was like, physics, whatever. I love bio, but as I gotten older, I can really, really appreciate physics, and especially things like quantum mechanics, which I find very, 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 very fascinating. So we're going to try to do an introduction into quantum mechanics. Um, but before we do that, I want to kind of go over some things that you've come across in high school, because these are concepts that we should have an understanding of before we get into a bit more in terms of quantum mechanics. All right. So first off, um, just let's talk about a little bit about light, because light came up in the last unit, special relativity. It's come up before. Um, Remember we talked about light being an electromagnetic wave. Remember when we did the animation about how antennas work? Basically the way an antenna works is it generates an electromagnetic wave, which is basically a wave that has an alternating, it generates a moving electric field, which generates a moving magnetic field, which generates a electric field. If you remember, Maxwell mentioned this, right? Like the electric field generates a magnetic field, which generates the electric field, and basically this moves at the speed of light. So light is a wave, but it's also a particle, and we'll come back to that. Light is a very, very interesting thing because it can behave as both a particle and a wave. And that's the thing about quantum mechanics, is things are just weird. Because we studied waves in grade 11, and remember we distinguished that waves and particles are two very different things. A rock and a wave are not the same thing. But you'll see when we get to quantum mechanics that, well, the line gets blurry, which makes quantum mechanics beautiful, but also very weird. Anyway, so we know what light is. We know it's an electromagnetic form of radiation. Now, the reason why I want to mention this is because this is going to help us understand some concepts that we're going to go over first, okay? Before we get into the origins of quantum mechanics. Okay, any questions about light being an electromagnetic wave? I think we're okay with that, right? And you can see that illustrated in this picture. Oh, I should mention one thing. Notice I think you can probably make this out. The electric field and the magnetic field are perpendicular to the direction of motion. So this is an example of a transverse wave. The particles, vibrate perpendicular to the direction of motion. Okay, so this is an example of a transverse wave. You can see that here. The other thing we should understand is the idea of wave interference, or something called superposition. Okay, this is actually another really important concept that's going to come up. You remember last year we talked about this, but we didn't go into that much detail. We just talked about wave interference. So for example, I can see here in this image on the left that if I take two waves, that you can see the peaks perfectly line up. So I can take a look at these two. When they perfectly line up, they create something like this, right? With something with bigger peaks, bigger troughs, because they're both in phase. What that means is you notice that the peaks and the troughs line up perfectly. Now, if we look at the next scenario, you'll notice that the two waves are not in phase. They're actually shifted. One of them shifted by we'll say half a wavelength or 180 degrees. Think about 360 degrees being a complete cycle. So a phase shift of 180 degrees would mean that if we line up one wave with the other wave, you'll notice that the peak lines up with the trough. So what happens in that case is you get destructive interference, right? The waves cancel out. So I think we talked a little bit about this last year in grade 11. I'm mentioning this because this is actually pretty important, what light is and waves interfering. Pretty important to our introduction into this, because we're going to talk about a few things that have to do with quantum behavior, and that is reflection, absorption, and something called emission, which I have over here. Okay, so let's start with reflection. Any questions, by the way, so far? How many of you took optics in grade 10?
I'm pretty sure all of us.
Yeah, unless you didn't get to that unit, you probably all did it, right? Okay, so, and you have experience with reflection. So if I said to you, okay, what's reflection, right? You probably would say, well, this sounds like something bouncing off something, right? Maybe light just bouncing off a mirror and hitting you so you can see it, right? Or often we think maybe a reflection of like an object hitting the wall and bouncing off. But at the level of what's going on at the microscopic level, it's actually a little bit more complicated than this. So when something is reflected, right, what we can say is that it's not being absorbed. You'll see later on that the term absorption actually means something different. So we're going to distinguish between reflection, absorption, and emission, right? These are important concepts. When something is reflected, it's not absorbed. So what happens is you see a particular color because those photons of light, they're not absorbed by the material, okay? So if something is like, for instance, like a shiny metal, it's probably reflecting a lot of visible light. So if it's white, that means it's reflecting all visible light. Copper obviously doesn't reflect all visible light because it's not white, it's brown, so it does absorb some color, right? So what happens when, like, for example, light hits a metal and gets reflected? What's actually going on, okay? So here's the explanation I came across, which I was like, wow, this is really, because normally you just think, okay, just the light just bounces off the material, kind of like, reflection, right? Just hits something and bounces right off. Turns out it's a little bit more complicated than that. So what happens is, okay, so a metal, if you remember, metals are good conductors, right? Which means that their electrons are free, so to speak. They can move around pretty easily. So what is light? Well, we know light is an electromagnetic form. It's an electromagnetic wave, right? So you have this electric field that's oscillating, a magnetic field that's oscillating. So what happens is when that electromagnetic radiation hits metals, the electrons start to oscillate, okay? And that's because of the wave that just hit it. Now, when they oscillate, they oscillate at the same frequency that the light hits it. So what happens then, if you remember from when we talked about antennas, is the electrons, when the electrons in the antenna move up and down, they create then electromagnetic radiation, right? Because you have now electrons going up and down. That's an electric field moving, right? Which creates a magnetic field, which means you're creating light. So what happens then is that you have two directions for this electromagnetic radiation: backwards and forwards, okay? Now, the one that's going backwards, that's what you see as reflection. Okay? So that's kind of interesting and a little bit bizarre, because you can see it's not just the light bouncing off the material, it's actually being kind of reflected back through a mechanism where the electrons are oscillating and producing an EM wave going the other way, and with the exact same frequency as the one that entered, or not entered, but hit the metal. Now, the forward radiation that's going into the metal is actually phase shifted by 180 degrees. So it actually looks like this. So what that means then, the light isn't going through the metal because it's being canceled out. So you have the light from the incident light, which is the source, that it gets canceled out because the electrons are vibrating, and that forward radiation actually cancels out the incident light, so you don't see anything. That's an interesting mechanism, right? It's very, very bizarre to think of. This is actually what's happening at the surface of the metal and going into the metal and being reflected off the metal. It's a very, very bizarre mechanism. Any questions about, so even something as simple as reflection seems not so simple, right? Seems like it's a little bit more complicated than just, it just bounces off a surface. So here's an interesting question. Can any electromagnetic radiation travel through a metal? So I came across silver. So apparently silver allows UV light to go through it. So I came across this video where person was saying that if you were placed inside a box that was made of silver, then inside the box would be dark. And think about this, okay? So inside the box, imagine a box that's made of silver, okay? And you were inside the box. And basically, you wouldn't see anything because visible light can't get through. However, UV light can. So what happened is you would come out sunburned, assuming that obviously it was a nice sunny day and that you weren't wearing sunscreen, that theoretically you can come out sunburned even though you were in a dark box, and that's because silver allows UV light to get through. That's kind of funny when you think about that. Lead, we know lead is very good at blocking out stuff. That's why you wear lead, for example, if you're getting an X-ray. So lead's very good at blocking out things like X-rays and gamma rays. I think it blocks gamma rays. I'm pretty sure it does. Visible light. I don't think it absorbs or prevents all forms of light from getting through, but it does absorb a lot more than silver does. Okay. All right. So let's not compare that to absorption. All right. So what happens when something is getting absorbed is different. Okay. So what happens when light gets absorbed by material is photon of light coming in. So here's my photon of light. Now, in the previous example, what happens is in reflection, the electrons oscillate, but they don't capture the energy from the photon. The photon makes them vibrate, which produces a backwards wave and a forwards wave. And the backwards wave is the reflection, it's what you see. In absorption, the photon of light actually makes the electrons jump to a higher orbital level. So the electrons actually capture the energy, assuming that the photon has enough energy to make them jump. Okay? So in absorption, the electrons capture the energy from the photon, and then eventually they emit it. So absorption actually and emission there's a symmetry between the two. Okay? So you'll see, and I think you probably learned about this probably in chemistry class, I think we may have talked about it last year. Do you remember the emission and absorption spectrum? I think we talked about it, right? So you can see, for example, this is the absorption spectrum for hydrogen. The black lines represent the energy. We'll talk about how to convert this into energy. We're going to get to that eventually. I don't know if we're going to get to it today. But these black lines represent types of energy from light, okay? And you can see that hydrogen absorbs certain wavelengths of light, which mean certain types of energy of light. And if I look at the emission spectrum, the colors that they give off are exactly the same as the colors that they absorb. And that kind of makes sense from even a classical physics point of view, because the amount of energy required to jump up a level is the exact same amount of energy that gets released when the energy comes back down, which is the color that would be produced through the emission spectrum, okay? So what happens then is electrons and atoms do require a certain amount of energy to jump orbital levels. This is called an energy gap. And again, when they absorb that energy, eventually they then emit it when they come back down to the ground state. So here's an interesting question then. Why is glass transparent? Now there is some reflection though, and now we know why. Because the electrons don't capture the energy, they do vibrate, and they send some radiation backwards. That's what you see, that's the reflection. But why is it transparent? Anyone want to take a stab at this? So you don't have to always just listen to me. Yeah, you know, talk here. It has to do, obviously, with what we just talked about. So we know metal is not transparent, but glass is. So what's going on? So it turns out what's happening is think of the electrons in glass. So let's imagine this is the ground state. And for them to get to an excited level, the next orbital level up, requires a certain amount of energy. It turns out that visible light does not have enough energy to make the electrons jump up one level. So what happens then is the electrons don't absorb the energy from the light, okay? It's just not enough. So what happens then is the light will go through the glass without causing the electrons to jump up over the level, so there was no absorption and therefore no emission. But that then leads to an interesting question. So if the electrons are not absorbing the energy and therefore not emitting it, obviously then something's still happening, because we know that when light goes through glass, it slows down. So why does it slow down? Now, this is a really, really interesting question. This one, I only came across the answer a little while ago. Not that maybe, I think it was last year or 2 years ago, because the explanation I came across before turned out to be wrong. And I guess you could say it's my fault. Maybe I should have looked into it a little bit more in detail. But there's a lot of explanations on the internet from pretty good sources where their explanations are wrong. They're just not right. So I'm going to show you something before I explain this, okay? And I think this link takes me here. Okay, so we know that when waves, meet up, they interfere. That's superposition, okay? So I want to show you, Okay, maybe I should kind of, this is kind of cool. I want to show you this. So here is two waves. So the blue wave that you're seeing is the superposition of the two waves on top. Now, you notice the two waves on top, they're moving both to the right. Can you see that? Now, you'll notice that they're not moving at the same rate, because I can see that, for example, the second wave, it looks like it's traveling a little bit faster than the first wave. So there's going to be times when the peaks line up, and there's going to be times when the peaks and troughs line up, and then you get like total destructive interference. Can you girls see that? But the two waves are not traveling, the two black waves are not traveling at the same speed?
Yep.
Okay. Now, I want you to look at the blue wave. See the blue wave that, I know sometimes it disappears, you don't see it, okay? But when you do see the blue wave, I want you to tell me what you think the speed of that wave is relative to the other two waves. In other words, is it like slower than, we'll call the top one wave 1, and we'll call the second one wave 2, and the blue one is the resultant, okay? So I want you to take a look at the resultant. I think I can draw here, hold on. So here's my, oh no, if I do that, then you can't see it anymore. So forget that, let's just keep going. Oh no, it disappeared. Let's do that again. Hold on a second. Let me, got rid of it. That's not good. Okay, hold on. I need to go back. But now I lost my notes. Oh no. Okay. I'm gonna have to get my note back. Okay, so where was I? I was here. Okay. Accident. Okay, so what do you think, girls? Isn't that blue? That's not the one. It was, I was showing you, yeah, this one. Okay, so what do you think? The blue wave. If I look at that blue wave, is it traveling, we'll call the top wave 1, we'll call the second one 2, and the blue wave is the resultant from wave 1 and 2. What do you think about its speed if I compared it to wave 1 and 2? Okay, let's ask the first question. Does it look like it's traveling faster than wave 1? So if I compare wave 1, the top wave, to this resultant wave, does that resultant look like it's traveling faster than the top wave? Rebecca, what do you think? You always got something to say.
I think it's the same speed, but I don't know.
Okay, look at the peaks. Look at the peaks in the blue wave, and then compare it to the top wave. And what do you notice?
They're the same.
Are you sure?
Are they? No, they're not. Never. I think the bottom one is a bit faster.
It is a bit faster. You can see that the peaks are slowly drifting to the right of the top wave. It's subtle, but you can see it. But if I compare it to the second wave, you'll notice that it's a little bit slower. Anyone disagree with that? I know you're going to say, I'm not getting any younger, my vision's not that great, my handwriting sucks, right, Monica? But I think it looks like that blue wave is faster than the top one, but slower than the second one. Anyone disagree with that? Monica, you're always fighting the
Okay,
man.
so
You're always
I don't know. I
fighting-
was looking
fight the
looking at
power.
it for a while.
What do you
It
think?
looks like it's the same for a bit, and then it like doesn't line up the same anymore. So I don't know.
But okay, I can't pause it, unfortunately. But you cannot see this peak traveling faster than this peak? Like if you were to follow
Oh,
it?
like the first one?
Yeah.
Yeah, I can see it's slower than the resultant one, but I mean like the second one.
Okay, so look right here. You see how this peak just started to pull away from it? Take a look. Look at the peak. Look how it starts to drift to it. So here, let's line up,
Oh,
for example. See how this peak right now, see how this peak is passing it? See that?
mm-hmm.
Okay, so what this means then is that that resultant wave, the velocity of that resultant wave is actually the average of those two waves. It's kind of in between. This is important, okay? This is important. This is really, really important. Now I have to get my notes back because I accidentally closed it. This is why YouTubers edit their videos. Okay, where was it now? Okay, right here. So we're back. Okay, here we go. Let's make this bigger again. We can see it. Okay. We were, well, I actually saved it. Wow, that's cool. Why does light slow down in glass? Okay. So what happens? Well, you have light coming in. We know the light doesn't get absorbed because the electrons need more energy than the visible light provides. So there's no absorption going on. But from the previous thing on reflection, we know what happens when that light comes in, which is an electromagnetic wave. It's going to cause the electrons in the glass. Imagine this is my piece of glass, okay? It's going to cause those electrons to vibrate. They're not going to absorb the photon and jump to another level, but they're going to vibrate, okay? Now, when they vibrate, we know that they can produce their own electromagnetic radiation, okay? So what happens is that the inside the glass, you have your incident light, but you also have the electromagnetic radiation produced by the vibrating electrons in the glass. And they produce their own light. But that light is not traveling at the same speed as the incident light. It's traveling slower. So the light that you see coming through the glass would actually be the superimposed wave, which is, now I don't know how many waves are being created in the glass. I have no idea. But it would be the average of all of the waves, which would be slower than the electromagnetic radiation coming from the incident light. Okay, questions about that? So I'm going to show you an explanation that I came across, and I won't mention the very famous YouTuber that actually used this explanation, but the explanation is wrong. And I came across another site, very good site. It's called, I think it's Fermilab with, I think the guy is Don Lincoln. Fantastic. And he explained why the one I'm going to talk about right now, why that one's wrong, why it's wrong. Now, any question about why light in glass is slower? So the simple answer is because there's many waves that are created in the glass. The resultant speed of light in the glass is a function of the average group speed of all of these waves, which is going to be slower than the incident light coming through air, which is almost like a vacuum. Okay. And by the way, I should have showed you what was it? Standing wave. This one actually has a standing wave too, and that's when whenever we talked about standing waves last year. For a standing wave to occur, you have to have waves traveling in the opposite direction. The one wave you see going to the right, the other wave is going to the left. Okay. This is a pretty good site. It's got some really neat animations. But anyways, okay. So let's go back to this. So the explanation I came across is something like this. So you have the light coming in, right? Now your piece of glass has atoms. Let's just draw a few atoms dispersed in the glass, okay? And what happens is that the and the photon light comes in, makes the atom vibrate, which then produces a light wave, which then maybe travels to another electron, which then produces a wave which travels to another electron, which then produces a wave travel another electron. In other words, it looks like the explanation kind of looks like what's happening is the light is just bouncing from electron to electron, and then eventually it goes out. Okay. And the explanation as to why the light is slower in the glass is because, well, that takes time, right? I mean, you have this light coming in, and the electron, the light is being passed basically from atom to atom, right? And that takes longer because you can see it's a longer path. So that means light's going to travel through the glass slower. Okay. What's the problem with this explanation, though? What do you think the problem is with this explanation? And by the way, the explanation assumes something that's incorrect, that the atom actually has to absorb the energy of light and then emit it as light, which it doesn't do. But there's another bigger problem with this model. Well, anyone want to take a guess? So let me maybe draw it as a two-dimensional sheet. So let's do this, okay? Let's say the model is the light comes in. Let's say the wave of light's coming in like this. Now, you know that light bends when it hits glass. That's if it's coming in on an angle. But if light's coming straight, then it doesn't bend. It just comes out like that, okay? So the model is, light would maybe get absorbed by this atom, get emitted to this atom, then get emitted to that atom, then maybe get emitted to that atom, then somehow end up being emitted in a direction that's parallel to the original direction. So obviously, what would be the problem with this model? Anyone want to guess? Mahi, I'm going to put you on the spot. What do you think the problem with this is? Is she even here? I thought she was here. Maybe she's not here. Oh, something wrong. Okay. Oh, laptop's having some trouble. Okay. Kristen, you want to guess? Well, okay. No, it's not an easy question, but the answer is really, really simple. Why does one atom pass the light to this atom? Why doesn't it just emit it like this? There's no reason why that atom has to pass the light to this atom. I mean, this atom, my diagram is passing the light to this. Well, why? It could emit it this way. This atom could emit it this way. In other words, the problem with this model is it doesn't explain why the light will travel in a particular direction. According to this, the light could be traveling in any direction, because if the atom is indeed absorbing the light and then emitting it, that's a random process. It could be emitting it in any direction. So you'd have light coming everywhere from this object, and that's not what you see, okay? That's not what you see. So this is not the explanation. What I mentioned before is the explanation, okay? About the average group speed of the light in the glass. Then it came across something else, because you go down a rabbit hole, right? So and then the question was, well, why does light bend in the glass? That has to do with obviously if the light is coming in on an angle. So we just explained why it slows down. So then why does it actually bend. And again, as I got this from Fermilab, and it's a fantastic explanation. It's the only one I've ever seen that explained it this way, which I think was great, because there are a lot of explanations out there that are wrong. In fact, the one that I've been using is wrong too. And when he talked about it, it's like, oh my God, I've been using that analogy. And it's not the right analogy. The analogy that a lot of people use is like, you have something like this, where imagine you have light coming in. Here's your boundary, right? So if it's going from air to water, what happens is it causes it to bend towards the norm. And the analogy that I've used, because not my own analogy, I've used it from other sources, is what happens where is like kind of like when a car is driving on the road. Imagine the cars on the road is like light traveling through air. And then what happens is maybe part of the car drifts off, and maybe the right side of the car, for example, hits maybe a patch of mud. Now, what's going to happen is that's going to cause the car to turn, because one side of the car is going to decelerate because of hitting mud, right? Now, that explanation isn't the right one. Doesn't explain really what's happening, because if that was the case, then what would happen is as the light turned, it would actually create sort of explained as a sort of like a torque on the light, which would cause it to actually travel faster than the speed of light, which can't be possible. So here's the explanation. Go something like this. Let me draw it actually as a straight line. So here's my incident light, and there's my refracted light. So we're talking about now refraction, not reflection, okay? Refraction is when light goes into the medium. So from our original diagram of light, we know that the electric field is perpendicular to the direction of motion. So I'm going to draw it like this, okay? Now this is just like a representation to explain it, right? So if that was our electric field, we can break it down into vectors that will look like this and like this. So I see a vector that's perpendicular to the norm. So there's the normal, okay? The surface. And I can see one that's parallel to the norm, all right? Now, if I do the exact same thing with my refracted ray, watch this. So here is my electric field, okay? Now, you'll notice that if I break it down into its components, this got a lot smaller. Well, at least I think it looks like it got smaller. And that shows you that the speed has decreased in that, I'll call it that y direction, that y component. And that relates back to what we just previously discussed. So you can actually visibly see that the light will bend because the fact that it's slowing down in that direction. That's a pretty cool explanation as to why glass bend. If you want to see it, it's look up Fermilab, why light bends in the glass or water. I think it might have been water he talked about, just to see that. So it's really, really, really cool. Okay, so anyways, we've been talking about absorption, talking about transparency. Why does light slow down in glass? Why does it bend? Let's talk about emission, okay? So what is emission then? Emission is the opposite of absorption, right? It's if an electron absorbs energy and jumps to a higher level, then when it comes back down, it releases that same energy. So for instance, let's imagine that a red photon, imagine a red photon of light hits an electron okay? Because you can see that there's, seems like hydrogen absorbs some red. So imagine a red photon hits an electron in hydrogen, makes it go up to another level. When that electron comes back down from the exact same level, what it will do is it will re-emit that photon of light in a particular, I don't know what direction, I would imagine a random direction, okay? And if it was to absorb, for example, blue light, so here you can see it actually absorbs some blue, and for instance, I think it's a violet color. What that means is that, and you should know this, that as we go this way, the energy increases. So that means the electron, but we'll model this in more detail. But if it does absorb sort of like a violet color or a blue light, that means the electron will jump to a higher level. So for example, if in this case it's going from, we'll call it the ground state, to the second level, call it the second level. And I'm not sure if this is the case, but just to give you an idea, then as it goes from the second back to the ground, it releases the same red light. If it absorbed, for instance, purple, maybe it's going like from the ground state to maybe like the fourth level, which is higher. So then if it comes back down directly to the ground state, it releases that same color of light. What's interesting, and we'll talk about this later on, is it does not need to go from fourth back to ground. It can go from fourth to third, but if it does that, then it actually would release a different color of light. And then as it goes from third back to ground, it releases a different color of light. But we'll actually talk about that, because we're gonna make those predictions when we look at the hydrogen atom towards the end of this unit. Okay, so we're gonna come back to that. Okay, so here's, this is an example of the emission, just heating something, right? So if you heat something, we know the atoms will vibrate. When they vibrate, the electrical charge is oscillating, so that produces electromagnetic radiation, like we saw in antennas, right? And remember, Maxwell talked about this. He said, that when you have an oscillating electric field, that creates a magnetic field, which creates an electric field, which creates a magnetic field that's traveling, at the speed of light. So a heated object gives off electromagnetic radiation. What it gives off is actually going to be influenced by the temperature. So the next time, because actually it's already 10 to 4, can't believe that, we will talk about what happens, we'll look at the emission of objects as they get heated, because it was the emission of energy as objects got heated that actually led to the entire development or the beginnings of quantum mechanics. And that is through the study of black body radiation. So why don't we end here? And the next time we get together, we'll talk about black body radiation and the start of quantum mechanics. Okay, girls? Yeah, let's stop here.